This podcast was produced from a webinar. For a more interactive experience with visuals, visit advancedmanufacturing.org/webinars.
Welcome to another SME Media webinar. I'm Carrie Gitter, Associate Editor. Today we'll be exploring the topic, why use a time series database for real-time industrial intelligence. This presentation is sponsored by InfluxDB, and we're joined by Scott Anderson, Product Manager at InfluxDB. Without further ado, now it's my pleasure to turn things over to Scott. Welcome. We're happy to have you join us today.
Thank you. I'm happy to be here. Thanks for the intro. I am Scott Anderson, as called out. I'm a product manager at InfluxDB, and today we're going to cover a few things. First off, we're going to talk about what time series data actually is, why it matters to you, how InfluxDB helps to address the very specific challenges that come with time series data. We'll have a brief demo and then actually go through some real life use cases. So what is time series data? And hopefully this doesn't feel too basic, but I think it's important to understand. Time series data is essentially any data with a timestamp where that timestamp is the primary dimension of that data. It's typically sequenced, the time order matters, and it generally comes from a single source or multiple unique sources. Everything happens in the context of time, so it makes sense that the time series data is one timestamp, is sequenced by time, but the importance of time series data is that it provides the context of time. It lets you see where things have been, where things are, and potentially where they are going. Yeah, here's two examples of somewhat everyday time series data types. We have weather conditions where we're tracking temperature over time. We have server monitoring. If anybody is familiar with the DevOps world, understanding what system resources a computer or a server is using is incredibly important and can help you assess the health of a system overall. Within time series data at InfluxDB, we typically divide it into two different categories. The first is metrics, and these are measurements that are gathered at regular intervals. So, for example, you're sampling a temperature every second or every minute, and you're storing that data in those regular intervals. This is what we refer to as metrics. The other category is what we call events, and these are measured at irregular intervals. These are points of data that were recorded when events happen. You can't predict necessarily when they're going to happen. They just happen, and you need to record it. One of the unique things about time series data and with metrics, they're really great because they happen at regular intervals. They're really great for forecasting data. Now with events, they happen at irregular intervals, but through aggregation and queries, where you gather points into a specific interval of time. And let's say you want if you're collecting if you're in a manufacturing process and you're collecting QA failures, every time a QA failure happens, you record it, you record why, you record the measurements associated with that failure. You can actually say, I want to know the number of QA failures per hour, and you then convert that irregular event data into regular metric data where you're reporting data per hour. And as you do that, you can then again very effectively forecast what can and what will happen within a system. Another thing about metrics and events is even though they're reported at different intervals or different types of intervals, they are almost always correlated. So as you're tracking both metrics and events and a phased process, you can identify correlations between what phase a process is in, events that occurred during that phase, and then the measurements that were regularly sampled during that phase. So this visualization, if you're familiar with web applications and traces, this shows how a trace works within a web application. It's essentially showing how an action propagates through an entire application. But you can identify you can identify correlations in both events and metrics based on phases or traces as it moves throughout the system. Now, this isn't unique to web applications or to DevOps. I mean, within the manufacturing world, imagine you have a cell on a robotic assembly line. There are several distinct phases to starting this cell. You have to power and initialize the control systems. You have to home your robotic arms. You have to load the raw materials into position. You calibrate your welding torches and your sensors. You run a test cycle. And finally, you begin the actual assembly of the assembly tasks like welding and painting or fastening within that cell. So as you monitor all of these different types of metrics and events that occur during each of those phases, you can very quickly identify correlations between things that are happening on the factory floor and anomalies that you may see within the metrics that you're collecting. So why should you care? Why is time series data important? We are firmly in the age of instrumentation. We have instrumented both our physical and our virtual world. According to just a quick Google search this morning, as of 2025, we collect or generate approximately 500 million terabytes of data per day. A lot of this is coming from web traffic, but as we're instrumenting both our physical world and our virtual world, we are collecting more and more data, and that amount of data is only growing. But for examples of instrumentation in our physical world, the devices that we carry on us, our phones, our watches, we have sensors that measure weather data. We have sensors all over our cars, sensors on our power grids, on our oil pipelines, things like that. We are putting sensors everywhere that are generating data that needs to be stored somewhere. And the same is true in our virtual world, our financial systems and our virtualized environments, our containers, our networks. All of these are being instrumented to provide information about what is actually happening within those systems. Now, the data that's being generated in the age of instrumentation is now the fuel for what I call the age of autonomous systems. And I think we are just in the beginning of this age. And I want to be clear in the distinction between autonomous systems and automated systems. I feel like we have a pretty firm grasp on automated systems, but when I talk about autonomous systems, I'm talking about systems that can analyze data and make decisions in real time without human intervention. They can truly think for themselves. And these systems are informed by data, but most importantly, they are informed by time series data. They need to understand what is happening and what has happened in the context of time. So everything from smart devices to our manufacturing lines to our autonomous vehicles, all of these autonomous systems are using time series data to understand what's happening within the system that they are controlling or within the environment that they're running in. So the fuel for the age of autonomous systems is the data that we've collected. I also want to talk about, I think this is especially relevant to the manufacturing sector, the idea of proactive versus reactive action taking, and potentially millions of dollars that it can save. To proactively make adjustments within a system, it requires change. We have to change how we are instrumenting our physical systems. We have to change the systems that are collecting that data and the pipelines that get that data where it needs to go. These new capabilities require changes to the systems that we have, and especially at scale. We need changes to those systems to manage the scale of data that we're collecting. Most legacy databases break with the amount of data and the need for real-time analysis of that data. Now, when it comes to unplanned downtime, in a survey conducted by ABB in 2024, it shows that in the manufacturing sector, downtime costs about $125,000 per hour on average. And within a data center outage, it's $506,000 per minute. So when things go down, there is a real cost to things being offline. Within that same survey, 21% of the 3,200 survey respondents said that they rely on a run-to-fail maintenance schedule, meaning they don't make adjustments until things go offline. This is really risky. And when things go offline, when they fail, they're hard to fix. So what autonomous systems and what the collection and monitoring of time series data allows us to do is understand systems, understands how systems are performing, and potentially forecast or predict maintenance before there's a failure. So you can minimize downtime necessary to fix any inefficiencies in a system. Now, time series data has some fairly unique characteristics. First and foremost, it's timestamped, and that timestamp is the primary dimension of the data. The value that it provides happens within the context of time. This data is generated in regular or irregular intervals. It typically happens or comes in huge volumes and at high frequencies, sometimes even millisecond intervals. We've seen volumes of data anywhere from thousands of data points to a second up to 1 million and even beyond of data points per second. So the amount of data that needs to be ingested when it comes to time series data is often very high. Time series data is also, it happens in real time and it's time sensitive. Often we see that the value of data, it lessens over time. So the fresher the data, the more valuable it is. We also see time series in almost every industry. Excuse me. Specifically, today we're talking about the manufacturing industry and industrial intelligence. But we see it in the software industry and software infrastructure. We see it in real-time applications. All of these applications are generating time series data and data that provides insight and context for how a system is performing currently and over time. But with these unique characteristics of time series data and the industries that it's being used in, there's challenges that come along with it. First and foremost is the massive scale of time series data. We are increasing the number of sensors that collect it or that generate it. We are increasing how often that data is collected and stored. This is just adding to the massive scale of the time series use case. Another unique challenge is real-time action, being able to query that data out of a system with as minimal time to be read or TTBR as possible. So as close to real time, as close to something happening when it happened, we need to understand that it was happening and take action in real time. Another really hard challenge with time series data, and this is related to the scale issue, but it's a different aspect of the scale issue, and that's what we call data cardinality. Cardinality is essentially the number of unique values within a data set. Specific to time series data, cardinality is typically determined by the source of that data. So you have tags within a data set that identify a unique source. So this could be a sensor on a motor or a rotary cutter or anything like that, a drill bit. But where that data is being generated, you typically have a part of your schema that identifies that source. The higher the number of unique sources you have, the higher your cardinality is. And in traditional relational databases, your cardinality is limited by your system resources. You need lots of memory to be able to handle high cardinality data sets. That's another really hard challenge with time series data. And the last is accessibility, the ability to access the data. A lot of traditional databases, a lot of general purpose databases essentially silo your data, and to to query and analyze that data, you have to go through the front door of that database. But there are so many other tools that you can use to analyze data in different ways. It's important to us at InfluxData to make sure that we leverage the openness of a data platform and make data accessible, not just through our database, but through other data analysis tools as well. So the unique challenges of time series data have led to the rise of time series as its own category. We have fairly established data categories. Relational, these are things like customer orders, just customer data or transaction records. Postgres is an example of a relational database. You have document stores that are great at handling high throughput and large document storage. MongoDB is the flagship document database. You also have search databases or vectorized databases, things that are great at distributed search, logs, geographic or geotemporal data. Elastic is an example of a search database. But time series, it is, as reported by dbengines.com, time series is the fastest growing data category by far. And part of the reason it's growing so fast is the time series is the type of data that sensors are collecting and need to store somewhere. So you can probably ask the question, why not use a general purpose database? Time series data is essentially relational data, but because of the unique characteristics of that data and the challenges it poses, it's not necessarily a good fit for a general purpose database. There are a handful of reasons, but these are the primary ones. First and foremost is the slow insert or write performance and the transactional overhead that generally takes place in a general purpose database. You also have the high storage costs. Most general purpose databases rely on traditional disk-based storage where you buy a hard drive and you pay for that hard drive whether you use the full capacity of that hard drive or not. And purchasing a hard drive can be a fairly expensive endeavor. You also have some fairly complex query execution, especially when you're querying by time ranges, how that data is structured on disk and how it's returned in a query plan. Things like that can get very complex with a general purpose database. Part of that is also the lifecycle management of time series data. Again, the value of time series data goes down over time. So it doesn't make sense to necessarily hold on to this raw high precision data over time. You need processes that can either downsample or evict that data when its value is no longer there. Within a general purpose database that's not baked in, that's something you have to do yourself. And another challenge you have with a general purpose database is just its ability to operate at scale and remain performant. There are databases out there that can scale fairly well, but they don't necessarily address the challenges that time series data offers or comes with. So when looking at the shortcomings of a general purpose database and what's needed in a time series database, it needs to be optimized for timestamp data. And it needs to be able to handle the high write throughput requirements that come with time series data, the ability to ingest and persist large amounts of data being written at regular intervals and intervals that can be quite short. You need queries that efficiently run over time ranges. You also need some automated lifecycle features that can make queries over time ranges more efficient. And then you need a system that is both scalable and performant at scale. These are required characteristics of a time series database. So I want to talk about InfluxDB and how InfluxDB aims to address each of these unique challenges. So InfluxDB is a time series database optimized for timestamp data. InfluxDB 3, our most recent version of InfluxDB 3, or of InfluxDB, is our is our next-gen columnar storage engine that's built in Rust and the FDAP stack. The FDAP stack is a collection of Apache-backed technologies that allow us to efficiently ingest, store, and analyze data at scale. Now, if you aren't familiar with the FDAP stack, these again are software. They're pieces of technology that are part of the Apache organization. Flight is a framework for efficient columnar data transfer. DataFusion is a highly performant SQL query engine. Arrow is an optimized in-memory storage transfer format, and then Parquet is an optimized, highly compressible storage format. So all of these allow us to perform high-speed ingest, enables InfluxDB to perform real-time querying with SQL. We have best-in-category compression with our data that has been persisted to storage. And then we also are able to perform bulk data eviction and transfer using these technologies. So with this implementation of technology, we have better performance and scalability. We have native SQL support out of the box. We eliminate any cardinality concerns. The limitations that you have in general purpose databases and even previous versions of InfluxDB when it comes to cardinality are no longer there. We have improved storage efficiency greatly. And then we've also enabled seamless integrations through the use of Apache-backed technologies and the open data architecture. You can leverage other data analysis tools to query and analyze data stored by InfluxDB. So there are multiple InfluxDB 3 products, but they're all based off of this same basic architecture. InfluxDB 3 essentially is comprised of around 6 different services or components, and each of these is dedicated to a specific task. The query service is responsible for processing query requests and returning results to a client. The write service is responsible for processing write requests and persisting data to storage. The compaction service optimizes data in storage and compresses it over time to make sure that the data that it actually is stored stored efficiently. These 3 services all interact with a catalog. The catalog is essentially a metadata store that stores metadata about the time series data. Most importantly is the physical location of that data within storage. So as a write request comes in and data is written, the writer will record where that data is being stored in storage and put that in the catalog. So when the query service comes in and requests that data, it first hits the catalog tells it where it actually exists, and the query service will go to storage and pull the data out. We also have a garbage collector, which is just that. It collects garbage. So anything that any data that's been deleted or has aged out, or any other artifacts that are no longer necessary within the system, the garbage collector will routinely take up. Now, a key differentiator of the InfluxDB 3 architecture is its use of object storage for its persistence tier. Object storage allows you to efficiently and affordably store data. So instead of having to rely on a traditional hard drive where you purchase the hard drive and you pay for it whether you use it or not, object storage allows you to leverage existing object stores like AWS S3, Azure Blob Storage, or Google Cloud Storage, and even there's open source options like MinIO. But you can leverage these technologies to efficiently and affordably store large amounts of data. Now, in object storage, we use Parquet to store the time series data. These Parquet files, part of the reason we chose Parquet is the ability to compress it and efficiently store it over time. Parquet just it does a few things. It makes storage more efficient, but it also is a format that is widely supported by multiple data analysis tools. So because we're using Parquet on the back end, you can use other tools that that support Parquet, things like Snowflake or DuckDB, to query that data and to analyze that data using those tools. One other unique thing about this architecture that was really important to us as we engineered this is the separation of concerns, meaning each of these individual components or services can be scaled individually. So let's say you have a workload that is heavy on the write side. So you're ingesting a large amount of data, but you don't necessarily have a heavy query workload. You can scale your write service both horizontally by adding more writers or vertically by increasing the resources available to each of those writers. But you can scale each of these services specific to your workload. The write and the query service don't have to share compute resources. They don't have to compete for those things to operate. They can be completely separate. And the same with the compactor and others. You can scale this architecture specific to your workload. And when you look at the write performance and the write path of a general purpose database, you essentially have a write request that comes in to record data and hits a writer service, and that writer service processes that data and persists that data to storage. In order for that data to be queried out, it first has to be persisted. So any data that gets written, a querier has to wait for that data to actually be persisted before it can query it. The problem is there is typically write latency in that process of receiving the data and persisting it to storage. And as you scale and as more data is written, that write latency increases. So the ability to read data in real time is harder and harder and harder. To mitigate this challenge, what InfluxDB 3 does is it introduces an in-memory queryable buffer in the write path. So as data is written to InfluxDB, it is first stored in an in-memory buffer that is available to queryers. Eventually, everything in the buffer is persisted to storage, but you don't have to wait for that persistence to happen before that data can be queried back out. Once it hits the writer and is stored in that in-memory buffer, that data is immediately queryable. So this reduces the TTBR. This allows you to query data in as real time as possible. A few other features that we've introduced with InfluxDB 3, and these aren't available in all of the InfluxDB 3 based products, but they are in InfluxDB 3 Core and InfluxDB 3 Enterprise. These are two different types of caches. These caches are meant to allow you to perform some common types of queries, especially with time series data, without having to do full table scans. So for example, with the last value cache, if you have a query where you only want to return the last reported values of specific fields, without this cache, you would have to query a specified time range and pull back all of the data that exists within that time range, and then limit those results to the last reported row per field. So there's a lot of inefficient overhead in that query process, where if you leverage the last value cache, it's a cache set up to automatically record the last recorded value for specific fields. So instead of having to do a full table scan, you're just querying those cached values. So the LVC is designed to return the last reported values in under 10 milliseconds. Distinct value caches, they function much the same, but for a different type of query. It's really common to query distinct values in what we call tags. Tags are what you use to identify the source of data. So for example, if you have weather data that's being collected from specific places around the world, and you're recording the country, the county, and the city, each of those would be tag values, and each would have distinct values that at some point you would want to query. So you can cache the distinct values of each of those columns within a distinct value cache without having to read the entire data set and then analyze it or process it to return those distinct values. Those distinct values just exist in the cache. And the distinct value cache is designed to return distinct values in under 30 milliseconds. So this is great for building UI experiences or custom applications where you're looking to return these distinct values for things like schema exploration, things like that. Another feature introduced in InfluxDB 3 is the processing engine. This isn't available in all InfluxDB3 products, but it is available in InfluxDB3 Core and InfluxDB3 Enterprise. But the processing engine is an embedded Python that can dynamically load and trigger Python plugins in response to events in your database. And a plugin is essentially just a Python script that can read, analyze, modify, and write data back to InfluxDB. Now, each plugin is triggered by what we call triggers. There are a few different types of triggers available with InfluxDB3. The first is a wall flush. This is any time that data is written to a writer, and then as it is taken from the writer and persisted to the object store, this is what we call a wall flush, you can actually process that data before it is persisted to the object store. So this is essentially modifying data on write. So if you need to process data, aggregate it in some way, update the name of a tag or anything that you would need to do on write, you can do that here with a wall flush. Another trigger is a scheduled task. You can use either a specified interval, or you can use a cron schedule to run these plugins on a specific schedule. And then the last trigger is on request. This essentially exposes an API endpoint that when you hit that API endpoint, it triggers the plugin to run. So it's essentially on-demand processing. Now, all of these plugins have a shared API that allow you to read and write line protocol, allow you to query the data, and also allow you to report any errors that occur. So this unlocks just a large amount of potential use cases, everything from downsampling data to monitoring and alerting on data, calling external services, predictive analytics, generating reports. All of these things can be completed through the processing engine. And part of the reason we chose Python as the runtime for the processing engine is because of the established data science pipelines that exist within Python. So this just unlocks a lot of power when it comes to processing data as close to the data as possible. So I have just a short pre-recorded demo that will just demo some of the features of InfluxDB3. Okay, so in this demo, I have InfluxDB3 Enterprise set up, and it is receiving data from a manufacturing process. This is a continuous flow process that consists of two stages. In the first stage, machines 1, 2, and 3 operate in parallel and feed their outputs into a step that combines the flows. Output from the combiner is measured in 15 different locations and then flows on to the second stage. In the second stage, machines 4 and 5 process the flow in series. After those are complete, measurements are again made in the same 15 locations. And this is a sample dataset provided on Kaggle.com, but we are replaying it as if it is happening in real time. Data is recorded every second and written to InfluxDB at that interval. Now in this demo, I've also configured a distinct value cache, primarily to cache the machine IDs and the measurement and location IDs. I've also configured a last value cache to cache the most recently recorded values of specific fields. I'm also going to show how you can use the InfluxDB3 MCP server to use LLM agents to interact with InfluxDB. If you aren't familiar with MCP servers, they are Model Context Protocol servers. They're essentially middlemen between an LLM agent and an external service. They instruct an LLM how to interact with an API. So in this case, the InfluxDB3 MCP server instructs an LLM agent how to interact with the InfluxDB3 API. Now in this demo, I'm going to use Claude, and I've configured my MCP server with Claude to analyze the data that is being written to InfluxDB3. This isn't limited to Claude. Any LLM agent, including OpenAI agents that support MCP servers, are able to do this as well. Okay, let's get on to the demo. So this is InfluxDB3 Explorer. This is just a UI for InfluxDB3. I have my database selected, my manufacturing database selected, and in that database I have 5 different tables. These represent all of the data that I'm collecting from my production process. You can see on a few of these I have caches configured, so I have a last value cache for the ambient conditions. And I'll just query these real quick, and you can see that the most recently reported values of humidity and temperature are returned. I also have distinct value caches configured for the machine IDs. I can query these real quick. These are all my unique machine IDs, and then I also have them for my measurement IDs, where I'm measuring the quality of the output of each of the stages. I'll just show the measurement IDs. So these are all my unique measurement IDs. And I can also just query the time series data. So if I want to query everything from ambient conditions from the last minute, this is the data that is being returned. So this is just InfluxDB 3 Explorer. It's a UI for managing InfluxDB 3 Enterprise. I've also created a Grafana dashboard that visualizes the data that we're recording. Now this is happening in real time. Again, we're replaying the data as if it's happening in real time. Right now this is refreshing every 30 seconds. Why don't we reduce the time range to the last 5 minutes, and we'll switch this to auto, and you can actually see that the data is updating approximately every second. Now, part of the reason I configured a distinct value cache was to be able to quickly and efficiently populate these variables. So I've set up this dashboard where I can modify queries to, in this case, only visualize specific measurement points. So right now I'm visualizing everything, but let's say I just want data from M0 and M1, and it'll update the visualizations to only show data from those measurement points. I can do the same with my machine IDs. Let's say I only want to see data from machine 1, and it will update all of the visualizations to only show data from machine 1. Now I'm going to change this back to a 30-second refresh interval. We'll go look at the last 30 minutes. Let's view all of the measurement points and all of the machine IDs. So you can see that this is a pretty robust dashboard that's reporting on this data. So this provides some really great information. I should say, for any of these cells where it's only visualizing a single value, instead of querying the entire 30 minutes of data and then returning the last value, I'm just using my last value cache. So this is just querying the cache and returning a single value for each of these fields. So again, these dashboards are really great for giving you a visual overview of what's happening in your systems. But I want to show you the power of leveraging AI to connect to and query this data and analyze this data in real time. So I have Claude here. So I've pre-populated a prompt for Claude that it provides some context for this manufacturing process. And I've also asked it to analyze the data that I'm storing in my manufacturing database in InfluxDB and identify any valuable or actionable insights. So I'm going to submit this prompt and let Claude run. I'm going to speed this part of the video up, but allow you to see as it operates. Okay, so Claude has finished its analysis. It's taken a look at all of the data that we've collected in real time, and it's provided some really important information. It's identified an urgent action that we could take, that there is a temperature control crisis in machine 3. It suggests some immediate actions that we could take. Some key findings in our data set is there's some quality hotspots. Specific measurement locations are exceeding our defined threshold. And it also identifies that there's a cascading effect throughout the entire production process. And it's able to identify this by analyzing the historical data. It makes a suggestion for a predictive alert. And it even suggests potential ROI of changes that we could make on alerting and acting on those alerts in the production process. So this just shows the power of using AI to analyze data in real time and perhaps draw out some actionable insight from that data. Thanks.
Thank you so much, Scott, for that very informative presentation. It looks like we have received some questions from our audience. And quick reminder to our attendees to get your questions in while we still have our expert here on hand. So let's take a look at what we've got. First question here is, why not just use a relational database or SQL database?
Yeah, and it's a great question and one we alluded to in the presentation. But there are shortcomings, especially related to the time series use case, that just general purpose traditional relational databases aren't able to handle. Again, it's the slow write performance, it's the complex planning that happens with time series queries.
Okay.
There's just some challenges that these traditional databases aren't able to address.
Got it. Thank you. Another question here. How much does influx data scale?
So that's an interesting question. I think it could be parsed in two ways. Like how much can you actually scale the database versus how much can the database actually handle? And both of those are somewhat the same. The answer is somewhat the same. So if you are familiar with the type of workload that you're running, InfluxDB3 can be scaled specific to that workload. So we've seen specifically on the write path, we've seen up to 1 million points processed. Now that can change. The write performance can change based on the schema of your data. For example, if you have data where you're writing 300 columns with every single data point, that's going to perform differently than if you're writing 5 columns on every different or every single data point. So that write performance can change drastically depending on your schema, but it really depends on your workload. The power of the InfluxDB3 architecture is that because all of the separate components and services are individually scalable, you can really customize the overall infrastructure to your specific needs.
Great. Another question here. What are some best practices to improve accuracy and performance with a time series database?
Again, this is really dependent on use case. I think understanding that when you write data, you have control over the precision of the timestamps and the precision of the values within that data. So really, you're essentially customizing the entire pipeline to your specific workload. InfluxDB is one of the few databases that supports up to nanosecond precision timestamps. That doesn't necessarily mean you are recording data every single nanosecond. We have seen use cases like that, but the vast majority of use cases don't necessarily use that level of precision, but that level of precision is available. So anytime you write data to InfluxDB, whether you're writing every second or every minute, the timestamp that is stored within InfluxDB is stored with nanosecond precision. So yeah, it really just depends on your use case.
Great. Got a couple questions here about InfluxDB. First one is, how does the new version of InfluxDB handle high cardinality?
So I guess to look at it, you have to look at the difference between the current version and the older versions. So with the older versions, to keep queries performant, we implemented an index. An index essentially is a cache that tells you where something is located physically within storage. So as you indexed by tag, the more unique tag values or tag value combinations you had, the more memory it required to maintain that index. So the amount of cardinality you could handle fully depended on how much memory you were able to throw at the database, which in many cases it became a limiting factor to the scale of InfluxDB in specific use cases. When you're looking at millions of distinct data sources, that cardinality can explode pretty quickly, and the memory demands to keep those query performance exploded in InfluxDB v1 and v2. With v3, we no longer use an in-memory index. We leverage a catalog, and the catalog is where the physical location is stored. And the catalog is optimized within the query path to quickly identify the physical location, but it's not bound by the upper limits of your system memory. With InfluxDB3 Core and InfluxDB3 Enterprise, the catalog is actually stored in object storage. We've optimized the queries to the catalog to make sure that it's always performant, but not memory bound.
Great, thank you. And question here is, can InfluxDB collect data from millions of data sources?
I think the short answer is yes, but I think there's two ways you could take this question. The first way is, could InfluxDB collect data from millions of unique data sources at the same time? Potentially, yes, it could. It depends on the schema of the data that's being written. It depends on the resources available to your write services. You would have to have a fairly substantial cluster of write nodes to handle something or a workload or a data pipeline that has millions of different data sources writing at once. But in theory, it's possible. The other way you could take this question is just the number of things that could potentially write to InfluxDB. So where you're actually collecting data from. So there really is no limit. InfluxDB3 and InfluxDB, all versions of InfluxDB3 make available client libraries that allow you to build custom implementations of data pipelines. So if you have something that you are pulling time series data out of, you can leverage a InfluxDB client library for your specific runtime, your specific programming language, and actually get that data in InfluxDB. We also have other data collectors. Telegraph is one of our most popular data collectors. Telegraph is a metric collection agent that essentially you install on a machine, and it will pull metrics from that machine or from a remote endpoint, convert it into Line Protocol, which is the write protocol for InfluxDB, and then store that in InfluxDB. Out of the box, I think Telegraph has over 400 plugins that can be used for either collecting or writing data or even processing data in the write path. So I think that, yeah, there's two ways to answer that question. Hopefully I answered both ways.
Great, thank you for the thorough answer, appreciate it. And see one more question here. This was kind of addressed during the presentation, but this attendee asked, how would you propose to effectively manage the aggregation, storage, and retrieval of high volume time series data? So maybe just to sum up, some of what you covered.
Yeah, this is a great question, and I think I'll address it in each of the separate parts, but I'm going to change the order. So first of all is the retrieval of that data, and I don't know. I guess retrieval could be querying the data. So why don't we talk about storage first? Obviously, to be able to query data, you have to store it first, but you need to make sure that storage happens quickly. So I had a few slides where it talked about the write path in InfluxDB3, and rather than having to wait for data to fully persist in storage before it's queryable, we first store it in an in-memory buffer, and you can query it from the buffer, but without having to wait for it to persist. That is how you get to as close to real time as possible. So I think that answers the effectively managing the storage part of that. And also related to storage is the actual format and structure of storage. If you're relying on disk-based storage, then you're gonna pay a hefty price for it. Where object storage provides a very scalable and cost-effective way to manage long-term storage. When it comes to retrieving the data, you need a high-powered query engine that is optimized specifically for time series data. I mentioned it a couple times, but time series, just the characteristics of time series data make query planning and query execution a little more complicated than you would typically get in a general purpose relational database. And when it comes to aggregation, this is where the power of the processing engine comes in. You have full control over the aggregation of that data. When it happens, how it happens, the precision that it happens at, you have full control. So the processing engine allows you to aggregate that data. We also provide other tools. Telegraph will, again, Telegraph sits on the right path. It collects data and then writes it to InfluxDB. But you can use Telegraph to aggregate data before it actually comes into the system. So if you know what aggregations you're going to need, you can pre-process that data before it ever lands in storage. But all of this needs to happen, again, at high volumes, intervals of less than 1 second. That requires a carefully architected, purpose-built time series database.
Great. And we have a follow-up question here. Would you leverage a key structure to relate this time series database back to your existing legacy relational databases?
You could potentially. Yeah, I mean, to join any type of data, you need a shared key. This could essentially be a tag value or even a timestamp could be your shared key. But yeah, you could leverage a shared key structure to relate time series back to existing relational databases. A really, I think, relevant use case here is like an asset management store where you're storing relational data for vehicles or for machines in a manufacturing line. That's a very different type of data than time series data, but those data sets are related, and you need to tie those back together. So yeah, you could use a key structure to relate that time series data back. A little preview into something that's further down our roadmap. I don't know exactly when this is coming, but we are planning on introducing what we call at this point static relational tables within InfluxDB. So you'll essentially have two table types. You'll have a time series data, and you'll have a table that is designed to store your traditional relational database, your traditional relational data. So instead of having to use an external runtime to query data from InfluxDB and from your relational database and combine it in that external runtime, you'll be able to do it all within InfluxDB itself. But that isn't available yet. That's something on a roadmap.
All right, great. And one more call for any attendees who want to toss in a question. Well, we've still got Scott live here. All right. Well, yeah, anybody who has any further questions, you can always follow up. And I think you'll see the link and information for reaching out to Influx in the webinar details. Oh, we've got one more. Oh, no, that's just a thank you for a great webinar, which it was. Terrific. So, yes, I want to thank Scott again and Influx Data for joining us today and sharing this very insightful presentation on a deeply relevant topic. I also want to thank our attendees for your participation and the great questions. We hope you found this content valuable and will join us again soon. Until then, remember that SME and SME Media are here to help you stay up to date on all things manufacturing. You can find links to podcasts, webinars, publications, and news by visiting us at advancedmanufacturing.org. Thank you for tuning in.